We now talk about arguments with quantified statements. We are going to first apply universal modus ponens and universal modus tonens. And let's begin with introducing this universal instantiation. So this rule says if some property is true of everything in a set, then it is true of any particular thing in the set. So basically, let's use this example to make sense of this rule. Say we say all human beings are mortal, so we have a set, which is the domain. And every human being in the set of this all human being, it says mortal, okay? So therefore, we now look at the second one. Socrates is a human being, so Socrates is one element of this domain, because all elements in this domain must be mortal, so this particular one must be also mortal as well. So this is what the universal instantiation rule. It is pretty, I would say, pretty intuitive. And another example that you may not be aware of, applying formula is a typical application of universal instantiation. So for instance, we do know like for a quadratic equation, we do know that like negative b plus or minus b squared minus 4ac over 2a, right? So this is a general formula. Now if you have a particular one element of this set, from this set, one particular quadratic equation, you can find its solution by applying this formula. This applies to the particular example, so which actually is essentially universal instantiation. The next one is universal modus ponens. The form of universal modus ponens looks like this. For all x, if px, then q of x, right? And this is major premise, a general premise. Now suppose p of a particular one is happening, p of a is happening for a particular a, and this is a minor premise, a specific premise. And according to what we know already, so q of a should be true. So when p of a happens, then q of a must happen. Please note that earlier we mentioned that the universal conditional statement can be rewritten as a universal statement by narrowing down the domain. In other words, if you see a universal statement, actually it is equivalent to a universal conditional statement by separating the domain into two parts. Okay, so we did this kind of practice earlier. So therefore, when you look at part B, all CSC majors are very critical. Now we can, because again, this actually is a universal statement, just like what we did up there. So we can actually use universal instantiation to derive the conclusion, or we can actually apply universal modus ponens. They are actually somehow equivalent. They two different forms. So here, if we apply universal instantiation, we say all CSC majors are very logical. Aaron is one of those CSC majors. Therefore, Aaron is logical, right? Aaron is logical. Or if you want to rewrite a universal statement into a universal conditional statement, we can do that. Like for all students, if a student is a CSC major, then he or she is logical. So now just rewrite this into for all if P then Q, this structure. And Aaron is a CSC major, so Aaron is P of A, right? So Aaron meets this condition. Therefore, this has to happen. Aaron is logical, so either way. Now, I would like you to read the use of universal modus ponens in a proof in the text, because we are going to use this next chapter. It's coming, okay? Now, the second one is universal modus tonens, which, if you can recall, modus tonens is the contrapositive, basically. So here's the form of universal modus tonens. For all x, if px, then q of x. Now, not q of a, therefore not p of, oops, there's a typo, therefore not p of a. So basically, it's just like contra positive. All math majors are hardworking. So now, if you remember, we can rewrite this as for all students. If a student is a math major, then this student, then he or she, right, is hardworking, basically, hardworking. Now, Aaron is not hardworking, so do you see that we are negating these parts, but with particular elements for students? So Aaron is not hardworking. Therefore, the result is we are going to negate this guy. Therefore, Aaron is not a math major. All right. So this is another example. Now, let's finish this first part of the video by applying the rules above to the following scenario. The first example is if an integer n equals 2 times k, and k is an integer, so if n equals 2k, where k is an integer, then we can conclude that n is even. So now we have a particular case. 0 equals 2 times 0, and 0 is an integer. So I would encourage you to try to make a conclusion. So here, this particular n is 0. So 0 equals, let me try to match those one by one. 2 times a k, integer k, and in this case, the k is 0 in this case. And now here 0 is an integer, right? This 0 is an integer. So that completely matches the assumption here. So therefore, we can conclude that then, therefore, we do not need to duplicate that then, just therefore, 0 is even. Now take a look at the second one. All healthy people eat an apple a day. So this is the major premise. Now, in order for you to apply one of the above rules, you gotta translate this into like if-then structure, if-then statement. So in other words, if you are healthy, then you eat an apple a day, right? So that's equivalent to that. Now, Tony does not eat an apple a day. So it seems like we are negating this particular one with a specific element, Tony. So Tony doesn't eat apple a day. Therefore, we are going to negate that. Therefore, Tony is not healthy. All right, this is the first part. In the second part, we are going to talk about using diagrams to verify some arguments, the validity of arguments.